Hello everybody, and welcome to our video on trigonometric identities. So let's go ahead and start off with the definition. What is an identity? An identity is an equation whose solution set is all values of x for which both sides of the equation are defined. So we're going to start out with a quick example. Show that sine of x equals 1 minus cosine of x is not an identity, which means that this equation is not always true for all x values in the domain. So, all right, let's just take a look. So first we're going to pick an x value that doesn't help us, right? So I shouldn't say the only way, but generally the main way we'll show something is not an identity is with a counterexample. So this is a really important distinction to make in mathematics. When you're saying that something is always true, that requires a rigorous proof that accounts for any possible value of x. But when you're showing something is not always true, you only need one counterexample. If I was to say all apples are red, all you need to do is show me one green apple to prove that I'm wrong. But if I say all apples are edible, I have to find every apple in the world and test them all out to make sure they're all edible. So the strength of your statement decides the strength necessary to prove that statement. In this case, showing something is not an identity just requires one counterexample. So I'm going to pick an x value that won't work though, initially just to illustrate. So oftentimes you'll try something and it's not going to be helpful here. So let x equal 0. So let's check sine of 0. Well, sine of 0 is 0. And 1 minus cosine 0 is 1 minus 1, which is 0. Are these the same thing? Yeah. So this is not helpful. And that's going to happen. When you're checking to show something is not an identity, and you start plugging in x values, sometimes you're going to get one that isn't helpful. That it actually shows that they can be equal. But being equal for a single x value doesn't mean that this is an identity. It would need to be equal for all x values. So let's try another. How about let x equal pi over 6? Okay, well then what do we get? Well, sine of pi over 6 is just 1/2. And 1 minus cosine of pi over 6 is 1 minus the square root of 3 over 2. And these two things are definitely not equal. So sine of x equal to 1 minus cosine of x is not an identity. Okay, so now when we want to prove identities are always true, we have various ways to do that. So some of these things are effectively definitions. So when we look at the reciprocal and quotient identities, if they're not actually definitions, they're so directly intertwined with the definitions. You know, cosecant of x, or cosecant of an angle is r divided by the x coordinate on the unit circle, and the y coordinate on the unit circle, and sine of an angle is the y divided by the r on our unit circle. So of course those are by definition the reciprocals of one another. So a lot of these identities are essentially the definitions of the things that they're talking about, or equivalent to those definitions. So reciprocal identities, quotient identities, and then we have the Pythagorean identities, which we've seen just come from applying the Pythagorean theorem, a squared plus b squared equals c squared, on the unit circle. And of course, we also have our even and odd identities. Sine is an odd function, cosecant is an odd function, tangent is an odd function, cotangent is an odd function, and cosine and secant are even functions. So all of these identities are really, really crucial for this material, because if we want to prove something is always true, then we have to use other facts that we already know are always true. And that means that these are our tool set for proving further trigonometric identities. So, at this point in the class, Hopefully most of these identities are memorized for you already. If not, I cannot strongly enough encourage you to start doing some flashcards, note cards, write these things down and start drilling them. Because if you can't recognize these identities immediately, if they don't come first thing to the top of your head when you're doing these problems, you're going to have a real hard time solving any of these problems. You really have to have all of the identities here on this page down pat, so to speak. So let's do another basic problem here, and then we'll dig into some verifying trigonometric identities problems. So here, example 2, use fundamental identities and the given information to find the exact values of the remaining trigonometric functions of x. So this is just saying, look, we have all these definitions or these identities here, reciprocal, quotient, Pythagorean. Use those to evaluate the other trig functions. So, for example, I know that cosecant of x is 1 over sine of x. So this is going to be 1 over the square root of 3. Division by a fraction is multiplication by the reciprocal. So this is just the square root of 3. Secant of x is 1 over cosine of x. So that's 1 over negative root 2 over root 3. I've just split this up instead of writing it all as one radical. I've written it as radical 2 divided by radical 3. So division by a fraction, again, is multiplication by the reciprocal. But typically, you will be expected to rationalize this, so you'll need to multiply by root 2 over 2. That gives us negative root 6 over 2. So tangent of x is, of course, sine of x divided by cosine of x. That's 1 over radical 3 divided by negative root 2 over root 3. And we'll rewrite that as multiplication by the reciprocal. And the root 3 over root 3 cancels. I get left with negative 1 over root 2. And of course, you'll be expected to rationalize. And now I can evaluate cotangent of x. I'm going to do this as 1 over tangent of x. Didn't say which identities I had to use. And I'm going to use tangent of x in the form negative 1 over the square root of 2, because that lets me just write this as 1 divided by negative 1 over root 2. Division is multiplication by the reciprocal. Put my negative in front, and I get negative root 2. So that saves me the extra trouble of having to re-rationalize if I was to start with this version of tangent. So again, this is nothing new. These are all types of problems you've done before, just refreshing on applying these identities to actually evaluate sine and cosine functions. But now we want to see how we can use these identities to start verifying future identities. So first we'll look at some guidelines. So generally, in a more, let's say, real-world circumstance, you would start with the more complicated side of the equation and attempt to transform it into the other side. Now, the reality is, when we're talking about an online homework system, you don't always get a choice as to which side you're going to start with, so keep that in mind. Now, as you're working through these problems, keep the final expression in mind because you have many different identities you can apply in the problems. So you need to actually be thinking about where am I trying to get to so that you try to pick identities and algebraic manipulations that will point you in that direction. So now consider the following possible approaches and keep in mind that these do not cover all possibilities. You can combine fractions together. You can factor things with the difference of squares. You can multiply by conjugates. That's like the opposite of factoring by a difference of squares, right? So you can multiply a fraction by 1 plus sine of x over 1 plus sine of x. 1 minus sine of x over 1 minus sine of x, so forth and so on. Now you could consider rewriting both sides in terms of sine and cosine, and then seeing if there's a different way to manipulate to verify these identities. But again, if you're working with an online homework system, you usually won't be given this sort of option. And as a last resort, you can simplify both sides. Again, not applicable to online homework. So with that being said, typically with a lot of online homework systems, you'll be stuck starting with one side and moving to the other side with these verification problems. So we're going to start with our left-hand side in all of these problems and see how we can manipulate towards the right-hand side. But I'm just trying to point out that that's not actually a rule or a requirement. You could start from the right-hand side and manipulate until you get the left-hand identity. But typically speaking, you'll be starting with the left-hand side for most problems you'll see. So, verify the identity. Sine of x minus cosine of x times sine of x plus cosine of x equals 1 minus 2 cosine squared of x. So what we're going to do is just think about what kinds of algebraic steps we can do on the left-hand side, and then what kind of trigonometric identities we can apply to manipulate to this side. So when I look at this, I see I have two things factored. Here I don't have two binomials factored. So that suggests one of the first things I should do is just multiply all this out. So I'm going to notate every step over my equality, just a shorthand for what I'm doing. And I really suggest as you start working on trig identity problems that you do this, because when you go back and look at your work, whether it's homework problems or practice problems, it's going to be a lot easier to figure out what you did and, relearn from those problems if you've actually notated which identities you were using along the way. So I start with my left-hand side and I multiply sine by sine, and I get sine squared of x. And I multiply negative cosine by sine of x. And I multiply positive sine of x by positive cosine of x. And I multiply negative cosine of x by cosine of x, and that gives me negative cosine squared of x. Now, here my middle terms canceled, and that should make sense because these two things up here were conjugates to one another. And that leaves me with sine squared of x minus cosine squared of x. So again, both of these steps, all I've done is a little bit of algebra. Now I want 1 minus 2 cosine squared of x. So I look at what I have, and again, every step of the way, it's good to pause and think, hey, what do I have? Where am I going? Well, what do I have? I have sine squared of x minus cosine squared of x. I'd like to have 2 of the second thing and none of the first thing. How can I replace sine squared of x? Well, this is where our identities come into play. So we know that sine squared of x plus cosine squared of x equals 1. So if I want to substitute sine squared of x, I can always rearrange this equation to be sine squared of x equals 1 minus cosine squared of x. That's going to let me just replace this sine squared. So I get 1 minus cosine squared of x minus cosine squared of x. And what did I use here? I used the Pythagorean identity. And 1 minus cosine squared minus another cosine squared is 1 minus 2 cosine squared of x. All right, so that's it for that problem. Again, as you're working through these problems, just think, where am I starting? Where am I trying to go? What kind of steps can I try in between to get there? Now, one thing to keep in mind is that you can do things that are correct that won't get you to this final step. That's really important. Like, for example, I could have replaced cosine squared of x with 1 minus sine squared of x, but that wouldn't have gotten me to this identity. So sometimes you'll take an approach and it won't actually lead you where you wanted to go, and that's okay. You shouldn't feel bad about that. You should just say, oh, that took me down the wrong path. I tried that. It didn't go where I wanted it to go. Let me erase it. Let me start over and try something different. That's perfectly fine. It doesn't mean that you necessarily did anything wrong, mathematically speaking. It just means that you didn't take a path that actually leads to the identity we're trying to verify. Okay, so moving on to another problem. Example 4 here, 1 over 1 minus cosine of x plus 1 over 1 plus cosine of x equals 2 times cosecant squared of x. All right, so we're going to start with our left-hand side. And what I notice is that I have two fractions on my left-hand side, and I have just one single term on the right-hand side. So that tells me I'd like to combine my fractions. So if I want to combine fractions, I'm going to need a common denominator. So what I'm going to do is multiply by the missing factor from the other fraction. So I have 1 minus cosine of x here. I'm going to multiply by 1 plus cosine of x at the top and bottom. And in my second fraction, the missing factor in my denominator is 1 minus cosine of x. What does this give me? This gives me 1 plus cosine of x plus 1 minus cosine of x, all divided by, and now when we multiply this out, well, I'll wait to multiply it out. First, we'll just rewrite it like this. So we've got our common denominator, and all we've done at this step is just a little bit of algebra. Now, cosine of x minus cosine of x cancels. 1 plus 1 is 2. Now if we look at our denominator here, I'm going to multiply the 1 by 1. That's going to give me 1. Going to multiply cosine of x by negative cosine of x. That's negative cosine squared of x. And the key here is that when I multiply my inner and outer terms, those are going to cancel. I'll get cosine of x and negative cosine of x. Those cancel, so I don't have to worry about those. And that happens because these are, again, conjugates that we're multiplying. Okay, so now I look at, what do I have so far? I have 2 over 1 minus cosine squared of x, and this is 2 cosecant squared of x. But if I think about cosecant squared of x, that's actually 1 over sine squared. So that looks a lot like this. So what do I remember? Well, I remember, again, that sine squared of x plus cosine squared of x equals 1. So if I subtract the cosine squared of x, it tells me 1 minus cosine squared of x is sine squared of x. So that tells me I can just substitute here using the Pythagorean identity and write this as 2 over sine squared of x. So again, sometimes you have to manipulate the identities you already have in order to use them, but that's perfectly fine. You're still applying that identity, you're just writing it in a slightly different form. And lastly, 1 over sine of x is cosecant of x, so 1 over sine squared is cosecant squared of x. So this is 2 times cosecant squared of x, and that's just the reciprocal identity. And that's my right-hand side. So we have successfully verified this identity. All right, let's move on to another example. So here we want to verify the identity cotangent squared of x plus tangent squared of x equals secant squared of x times cosecant squared of x minus 2. And there's a number of ways that I could try to solve this one, but one of the things that comes to mind immediately, and these come to mind a lot, is the Pythagorean identities for cotangent and tangent, because I know that 1 plus tangent squared of x is equal to secant squared of x, which means that I can rewrite tangent squared of x as secant squared of x minus 1. And similarly, 1 plus cotangent squared of x is equal to cosecant squared of x. So cotangent squared of x equals cosecant squared of x minus 1. So the reason I bring this particular set of identities up, or why I would think about using these identities, is because my goal is to take two functions that are written in terms of cotangent and tangent and rewrite them as functions of function of secant and cosecant. So that's exactly what these Pythagorean identities do. So that's what I'm going to do. I'm going to give that a shot and substitute those in, see what it gets us. So when I plug in cotangent squared of x in place, I get cosecant squared of x minus 1 plus tangent squared of x, which is secant squared of x minus 1. So that's just Pythagorean identities. And so this gives me cosecant squared of x plus secant squared of x minus 2. Now, it's pretty easy to look at this and think that you've done something wrong, to be honest, because it's like, hey, I should have secant squared of x times cosecant squared of x, but I've got cosecant squared of x plus secant squared of x. But that's okay. That just means we have more manipulation to do here. So that step was just a little bit of algebra. So what I'm going to do is use my reciprocal identities here to rewrite cosecant of x as 1 over sine of x. So this gives me 1 over sine squared of x. Plus, I'm going to rewrite secant squared of x as 1 over cosine squared of x. And I've left myself a little bit of space here because I've got two fractions now. And I don't want two fractions. I want to combine these into a single factor here. So I'm going to do that by multiplying by my missing denominator here. So for this first fraction, I need cosine squared of x. So I multiply the top and bottom by that. And for my second fraction, I need the factor sine squared of x. And so now we've got a common denominator of sine squared of x times cosine squared of x. And up top, we get cosine squared of x plus sine squared of x. And we've still got this minus 2 off to the side. So again, here, all we did was some algebra. Now, I know that cosine squared of x plus sine squared of x is 1. Right? Cosine squared of x plus sine squared of x equals 1. So I can replace that and rewrite this as 1 over sine squared of x times cosine squared of x. Still have this minus 2. So all I did there was use my Pythagorean identity for cosine and sine. As you can see, you will use those Pythagorean identities a whole lot when you're trying to verify these other identities. Okay, now we have 1 over sine squared of x times 1 over cosine squared of x. And 1 over sine squared is cosecant squared, and 1 over cosine squared is secant squared. So this is cosecant squared of x times secant squared of x minus 2, which is the same thing as my right-hand side. And all I did there was use my reciprocal identities. Okay, well that's it for that one. Let's go ahead and move along. All right, example 6 here. Verify the identity cosine of x divided by 1 minus sine of x equals secant of x plus tangent of x. So again, we always want to start out by thinking, okay, what do I have? Where am I trying to go? On the right-hand side, I have two separate terms added together. On the left-hand side, I have a single fraction. So somehow I'd like to be able to rewrite that fraction as two separate terms. That's not really possible right now. And so that becomes a little bit trickier. How can I maybe rewrite my denominator instead of 1 plus or minus something? It's just a single number. Well, if this had been 1 minus sine squared of x, I could use a Pythagorean identity. So how could I maybe get there? Well, what I could do is take the 1 minus sine of x that I have, and I can multiply the top and bottom by 1 plus sine of x, the conjugate. Now in the denominator, when I multiply the conjugate, that gives me 1 minus sine squared of x. Again, we get 1 times 1 is 1, negative sine of x times sine of x is negative sine squared, and then the inner and outer terms, negative sine of x and positive sine of x, cancel. Meanwhile, in my numerator, I have cosine of x times 1 plus sine of x, and I'm just going to leave that as is for now. So just a little bit of algebra there. Okay, and now let's take a look at our Pythagorean identities again. Sine squared of x plus cosine squared of x equals 1. Here in the denominator, I have 1 minus sine squared of x. Well, if I look at my Pythagorean identity, if I move sine squared of x across, I see that 1 minus sine squared of x is cosine squared of x. So that lets me rewrite my denominator here. As cosine squared of x. So now I've got a factor of cosine up top and 2 factors of cosine in the denominator. So cosine over cosine squared just leaves a single cosine of x in the denominator. This gives me 1 plus sine of x over cosine of x. Okay, again, all we've done so far really was just apply the Pythagorean identity at this step and a little bit of algebra at this step. Now, I should pause, because again, after every step or two, you should really pause and say, wait, where am I going again, and how do I get there? So I tried out this multiplying by the conjugate, and I did the natural simplification that occurs there, and now I'm stopping and I'm going, okay, I've got 1 plus sine of x divided by cosine of x, but I want 2 separate terms. Well, that's fine. Just split up your fraction into 1 over cosine of x plus sine of x over cosine of x. Again, that's just a little bit of algebra. And now 1 over cosine of x, that's the reciprocal identity. That is secant of x. And sine of x divided by cosine of x is the quotient identity. It's equal to tangent of x. So now we use the reciprocal and the quotient identities. And that's our right-hand side. So we're done. Now, before we get to our last example, I just want to reiterate something here. These problems are going to seem really easy when you're watching me do them for the most part, because I know my identities really well. And when I look at these problems, I know, oh, that looks like this identity, this looks like that identity. When I see 1 minus sine squared of x, I don't really have to think about that. I know that that's cosine squared of x. I know that that's one of my common identities. When I see 1 over cosine of x and sine of x over cosine of x, I immediately think of these as secant of x and tangent of x, respectively. So the point being here, that only comes from studying these identities a lot. Just practicing these identities until they're automatic. That's really, really important. You really have to build a mindset where whenever you see any of these expressions, 1 over secant of x, your brain immediately fills in, oh, that's cosine of x. Cotangent of x equals cosine of x over sine of x. Oh, right? You see cotangent of x, you're also thinking of it as cosine over sine. There's no magic trick here, right? Like a lot of times people want a magic trick. What's the secret that I'm going to say where you just instantly will remember all of these? There is none. These are definitions. You just got to sit down, got to get some note cards, or just write them over and over again. And whichever method you prefer, generally, I find that Using note cards as a quizzing strategy is the most effective, where you quiz yourself. You see reciprocal, identity, secant of x. And you go, okay, that's 1 over cosine. You flip it over, you check. You've got 1 over cosine on the back. Did you get it correct? If not, try it again. Put it back in the pile. And just keep practicing those over and over until they're all really automatic. That's going to make all these types of problems so much easier. Okay, with that all out of the way, let's go ahead and take a look at our last example here. Make the indicated trigonometric substitution in the given algebraic expression and simplify. So this is our algebraic expression, the square root of 1 plus x squared. And we're given that x equals tangent of theta. Now, I should have added a little restriction here, something like theta is between 0. That should actually, well, yeah, it can be inclusive for 0. 0 and pi over 2. Just to ensure that tangent of theta is positive, because we're going to take a square root of, well, it's really going to ensure that secant of theta is positive. Anyways, point being, when we take a square root, it'll ensure we're taking the square root of a positive value, and that the answer we get is going to be positive. So that little condition should have been in the statement of the question as well. Okay, so with that being said, I take my square root of 1 plus x squared. All I'm doing here is just substituting x equals tangent of theta. So I just replace the x with tangent of theta, 1 plus tangent of theta squared, and we generally write this as just 1 plus tangent squared of theta, right? It's the same thing. Now, 1 plus tangent squared of theta is secant squared of theta. So when I use my Pythagorean identity here, I get the square root of secant squared of theta. Now, since I know that theta is in the first quadrant, I know secant of theta is positive. So when I take the square root of this squared function, I just get this positive secant of theta. And that's it. So this may seem like a simple little thing and an idea that isn't, maybe it doesn't seem that important, but actually this kind of manipulation comes up constantly in Calculus 2 and in application problems, where in order to be able to evaluate certain integrals, which that statement is not going to be very meaningful right now in your mathematical career, but in order to evaluate certain integrals, you need to be able to do these algebraic manipulations and simplifications with this kind of trigonometric substitution. So this is actually going to come up a lot, so it's worth practicing and making sure that you've got a solid grasp on it. Okay, well that's everything for this section. Thanks for watching.